you help me, if my video drops, if my audio drops out, or video drops out, Nick, you can text message me, or and if you guys can make a little bit of noise once in a while, just for me to make sure. I've given talks to internet outages before, so I gave a it was frustrating. I gave a talk for an AI conference for NASA, and every time you talk about AI for NASA, you're guaranteed to get some sort of ironic technical glitch. All right.
And Barbara, do you want to introduce yourself?
Okay, so I'm Barbara Thompson. I have worked at NASA Goddard Space Flight Center for 27 years, over 20 of them in this very office. And I work on solar dynamics. I've worked on a variety of programs. I've over those years helped to develop some missions, did a lot of space weather research, and served on the committee that did the International Heliophysical Year and established the field of heliophysics. So I was very happy to see a lot of you consider yourselves heliophysicists. I was very welcome to our community. Is that good enough, Nick?
That was great.
All right, you can see my screen okay?
We can.
Okay, then I will close out this. And anyways, and so I think I can give the talk, but why would I give the talk when we can sing it? I don't know if you guys have seen this.
There once was a star in a galaxy, it was named the sun, and thankfully it weaves a solar tapestry, since particles high and low. Soon may the solar wind come to bring us plasma and magnetism, filled with hydrogen and helium, and the solar wind will blow.
The solar wind charts a course, pulling lines of magnetic force, flowing outward from the source, throws particles to and fro.
So I'll post that in the chat later on, everyone. That's some of my colleagues here at NASA Goddard, and they did this wonderful performance, a scientifically accurate story of the solar corona and solar wind. Let's go through some very general topics of solar corona and solar wind physics. So there's the structure of the sun. Where did the corona and solar wind come from? It starts in the interior. It moves out to the photosphere and solar atmosphere, and it is a function of the magnetic features of the corona. Now, I'm just going to go through, I'm not going to explain all of these. My talk has a bunch of these things in it, but if you want the very short description, it comes from the structure of the sun. The solar corona is a function of magnetic structures and different magnetic features, and also the processes that cause the corona to be so hot. The basics of the solar wind, to put it very simply, there are kind of two general domains of solar wind. There's high speed and slow speed. And the interesting thing happens kind of at the transitions and the boundaries between the two. And finally, there are many time scales of variability. There's short-term variability, there's large-scale processes like flares and CMEs, and there's small-scale processes that happen on the short term. There's also intermediate term, which solar rotation and the evolution of these large features happen on the scales of days to months. Finally, there's long-term variability. The solar cycle varies, and you can have variations on the scale of decades to years. All right, so let's go a little bit slower, but not too much slower. The solar magnetic field is generated in the sun's interior. The solar magnetic field extends to form the solar corona. The corona is much hotter than the visible surface of the sun, which is called the photosphere. The source of the heat we know is magnetic in nature, but the exact mechanism is still under debate. The corona expands to form the solar wind. The extended domain of the solar wind goes out far past the planets beyond 100 AU, and this is called the heliosphere. Now, what I'm telling you is all things that you can find in these wonderful textbooks that were designed by, that were written by some of the greatest experts in our field. And so I will just go through this pretty quickly, and then I'll go into some more details. Anyways, so nearly all of the variations in heliophysics are due to the solar magnetic field. And this is outside of the Earth's atmosphere. There are some Earth's atmospheric processes, but even then, the variations in the solar wind are a big part of these processes. Fortunately, we had the wonderful talk from Dr. Guhathakurta yesterday, who covered some of these variations, the space weather processes, and also, if you remember, El Nino and La Nina for the sun, the differences between solar minimum and solar max, and why these space weather interactions are always happening. And so I will talk about some of these intermediate timescales and some other processes. I will focus on those. There are general timescales of these variations in the that are as a result of the solar varying magnetic field. Again, the solar cycle runs from solar minimum to solar maximum, and people kind of say it's 11 years, but really the solar cycle can be between 9 and 13 years from all together. Some people also call it a 22-year cycle, because the polarity of the magnetic field of the sun flips and they wait for it to return to its original polarity. However you may call it, a standard way of measuring the solar cycle is the sunspot number, but there are many manifestations of the solar cycle. The cycle itself also varies over millennia. There have been long periods of dormancy observed. On the timescales of minutes to hours, we have flares and coronal mass ejections, which Dr. Guhathakurta talked about yesterday. And they're examples of energetic phenomena, large-scale energetic phenomena caused by the release of magnetic energy. They originate in the solar atmosphere, but there are impacts on the solar wind through varying phenomena, and you will learn about some of those impacts tomorrow. And there are certainly impacts on our planets. Whether those planets have a magnetic field or not, there are impacts on planets. And there are also small scale transients on short time scales. And we are becoming increasingly aware of the importance of those small scale transients in determining how the structure evolves and the fundamental processes governing the solar wind. Are you guys all still with me?
Yes.
Yes.
Yeah.
Wonderful, wonderful. And I will provide these slides to you. These are Google Slides, and so you guys can see these, and you can even copy them if you want to use any of them yourselves and improve on them. On the time scale of months, however, there are also very important variations. Sunspots, magnetic active regions, coronal holes, I'll show you some in a little bit, are examples of solar magnetic features that govern the large-scale structure of the sun, and they evolve over the time scale of days to months. You also have learned that when there are large releases of energy, those releases can happen over the course of seconds to minutes. But when they are not, even when they're not erupting, they're evolving. And the time scale, you can watch coronal holes persist for many months. Magnetic active regions, as sunspots decay into magnetic active regions, those can persist for months. And the evidence of those former regions can stick around for years as the magnetic field becomes more distributed over the surface and less concentrated like they were when they first emerged. Another intermediate timescale process is the sun's rotational period. It's about 27 days. It's a big ball of gas, and so it's not a perfect, it doesn't rotate as a perfect sphere. However, the solar wind is when the solar rotation causes the solar wind to go into what we call the Parker spiral. And because it is not homogeneous, it has what we, you will see things, sometimes people describe it as a ballerina skirt. It has kind of fluted structures. It can also have other very large scale structures that become even more important as we go farther out into the heliosphere. It's the variations in the source of the solar wind with, again, this kind of general realm of high speed and slow speed that cause the heliosphere to have this very interesting structure, even in the absence of any eruptions, any transients. So the combination of long-term to short-term to long-term variations have a range of observable impacts at the planetary magnetic environments as they propagate through the heliosphere. And as you learn more about processes at Earth, you'll start to see how the Earth and the planets have a response to these variations. Are we good?
Yeah.
Okay,
Yes.
great, great. Sorry, I can actually, I believe I can, let me see if I can move this to my other screen, and then you guys can, there we go. Now I'll see you guys in my other monitor. I apologize for not having that there at first. Anyways, so everything kind of begins in the solar interior. I want to get us to the corona, but first of all, the energy of the sun comes from the sun's core, generated by thermonuclear reactions. And this, outside the core, there's a region called the radiative zone that goes out to about 70% of the distance from from the center of the sun. And energy moves outward. It's just photons moving around, and it's supported by the pressure. But the interesting thing about these photons that were generated in the core, they can take over 100,000 years. The estimate is 170,000 years to radiate from the core to where we would observe it as a photon leaving the sun. The convection zone is the zone that we start to be able to observe well, because this is the area where we have currents that are heated by the interior, and as they rise, they get cooler. And this is very similar to what you'll see in a pot of boiling water. The energy continues to move to the surface, and these convection currents these flows and shears in the interior are what causes the solar magnetic field. And so right here is where you would observe a sunspot that is the result of the processes in the interior. So this is a fascinating thing. It's covered very well in your textbook, and that's not my job. My job isn't to tell you about the corona and about the interior. And so the innermost layer of the sun that we can see directly is the photosphere, and it's called the photosphere because we are observing it in regular light. We can see, that's how we see the sun. This image is a special filter. Now, you will hear a lecture this afternoon, or I guess depending on where you are, it could be you'll the next lecture will be from Dr. Landi, who is one of the greatest, most experienced observers of solar phenomena that we've ever had. And so you will learn all the different ways you can observe the sun. So I'm going to throw lots of images at you, and I will and I look forward to I hope you'll forgive me for not explaining these in super detail. Dr. Landi will go into this extremely well. So we see this observed invisible light, and with if we have a high resolution telescope, we can see little small cells. We call that granulation. Then it's due to the underlying plasma convection, and this is what a sunspot looks like whenever you see it in high resolution. There's this region called the umbra, and then there's this dark region, which is due to strong magnetic field. And this sunspot's a large one. It's a little larger than the size of the Earth, all told. And so sunspots arise as a result of the emergence of strong magnetic fields from the interior that make it into the surface. Now, again, there are many ways to observe the sun, and we are living in the outermost atmosphere of this magnetic variable star. So there are many ways to view the sun. And I just have two right here. These are, this is just now, this is what the sun looks like, or just from, I guess, from 2 days ago. You can see that the sun has some nice sunspots on it. And this is what the magnetic field looks like. And so green and blue are, the red and yellow are when the loop comes out of the sun, and green and blue are when the loop comes into the sun. So we're seeing magnetic loops. And if you're a big fan of solar structure, of course, do not miss the solar eclipse coming up if you're in the United States. If you're not near there, it's going to be a little tough to view that. I'm sorry, this thing is, can you go away? Thank you. All right. Anyways, and EUV and X-rays now, if you look in those wavelengths, you get to see the super hot corona. And so we had the photosphere, and now we're moving out to the corona. Now I'm going to put the magnetic field on this image so you can kind of see that most of these structures that we observe are related to that magnetic field. You can see that there are loops. There are loop structures. There's something we call a filament channel, which is a large scale magnetic structure. And you can even see coronal holes. These are regions that are dark because the plasma is streaming out, and these are the source of high-speed solar wind. So we have these different structures, and all of these, the whole magnetic field from the small scale to the large scale as we observe it, combines to form this large scale solar corona. All right, so we've got lots of features. We've got things, these active regions can have flares, they can have eruptions. Filament channels can also have eruptions. And coronal holes, again, are sources of steady flowing plasma out to the heliosphere. So all of these things are examples of phenomena on the sun that can have impact on the heliosphere and on the space weather processes at the planets. All right. So why is the corona so hot? There are several candidates. I put them in here just
Hey,
for.
Barbara.
Oh, yes.
I'm sorry to interrupt. There's a couple of questions in chat.
Oh, sure.
So the one goes back a little bit to the interior of the sun. I don't know if you can answer this or not, but are the element abundances different in different regions of the sun?
Yes, absolutely, absolutely. In the core, that is hydrogen burning to helium and then beryllium. And so these are, so the chain of the reactions at the core are where you're getting these dominant processes happening. But there is some stratification in composition. Now, it's a little difficult because we have to depend on models. The photosphere is the visible surface of the sun, but we can watch things. We can watch the sound wave motions. We can see Doppler shift on the surface, and believe it or not, if those of you who are not familiar with the sun, we can take scientists take those Doppler signals and invert them and infer the interior structure. And so there are models of the sun that include different elements in structure. Now, Dr. Landi will get into this, but this, for example, this image here, this outer image that I have here, this is made from emission lines of helium-2. Helium is it's a singly ionized helium-1 is transition lines in neutral helium that hasn't lost any electrons. Helium-2 are transitions in singly ionized helium. And doubly ionized helium means there's no electrons, no transitions, and no photons. And so this is a very strong emission line in helium-2, for example. And then we can look this thing here now, that's iron-12. That's iron that's been ionized 11 times. And so it takes a lot of heat to ionize iron many times. That is why you can see the corona, the very hot corona with iron, but there's not much emission at the photosphere due to this iron line. Or at least comparably compared to the visible light emission at that temperature. Now that's kind of complex. So yes, there is stratification inside the sun, and there's certainly a stratification in the solar atmosphere. And this stratification continues outward into the heliosphere. There are some really interesting effects by which the heavier elements of like iron and nickel and things, they are less, that's more difficult for them to leave the sun because they have more gravitational potential. And so there are processes where we study the sources of the solar wind, if they are in terms of just these coronal holes, or if they're in terms of a large magnetic blob that leaves the sun. And we look at the composition of these things to figure out more about the processes that cause the magnetic processes that cause those things to happen. So I'm sorry, I don't, it's a lot, I apologize, but you know, you'll learn from Dr. Landi, observing the sun, it's all about photons, photons, photons. We're very creative with photons. But there's a lot of elements that we've observed, and the different abundances of the elements are very important for our understanding of the basic physical processes. Was there another question?
There was another question about looking at the sun under smoky or cloudy conditions, and I think I'll just say that, yeah, you can. There's historical evidence of people observing the sun through haze and seeing sunspots, but please don't do that. It's a bad idea. Just because of if you do it without any special eye protection or projective equipment. So
Yeah, well, I gotta say, the most dangerous time to observe the sun is during a solar eclipse. And the reason is because when you're looking at something bright, it's kind of the integrated flux that hits your eye that causes your pupils to contract. But a solar eclipse isn't super bright, but there is but there are little, especially when the moon is not quite covering it, just when it's going into or out of the eclipse, where you can have something as bright as the sun, but only focusing on a little part of your retina. And so the rest of your eye is perfectly fine and your pupils don't contract as much. And so it doesn't limit the flux as much. And so the most dangerous time is eclipse, but yeah, don't stare directly in the sun. Get some glasses, get some glasses from reliable vendors, I should say. Yeah, so I'm sorry, did I answer those two questions okay? I apologize for being so brief. I think
that sounds fine, and the chat's been active too.
Okay, the abundance with is an excellent thing for Dr. Landi to cover. He's really creative with different abundance and photons to study the to solve fundamental problems. Anyways, and so we have a lot of solar structure, and I will not cover that so much because I've got to get on to the solar wind too. And again, I will share this presentation with you. But there's an interesting problem. The photosphere is much cooler than the corona. Now, all the heat is coming from the interior. All the energy is coming from the interior. So why is the visible surface of the sun much cooler than the corona? The visible surface is thousands of degrees. Corona is starting at 1,000,000 degrees. And so, and there are several candidates. I can tell you that if you study coronal heating, it's a steady job. People have been arguing about this since before I was born. They'll probably add it after I'm gone too. And so it's a good job to have. And they're fun, they're a nice community. And so you can, and there's many different, you can have wave heating, you can have impulsive heating through small scale explosive events. And you can also have a kind of a hybrid where you have turbulence, the conversion of large scale to small scale, and the heating and these fluctuations can heat the corona. One example is these, if you have nano flares, these small scale reconnection events where the magnetic field has small scale releases of energy. These are on different spatial scales, but they're in general, you know, this is a model, and it shows the and it shows a zoom in of just a single magnetic active region of the sun, and showing that how these small scale releases can happen. They're called nanoflares because they estimate that 10 to the 9th, they're about 10 to the minus 9th the size of a typical flare. In other words, they're very small scale but steady releases of energy. And again, that's one of the contenders. I like to tell my students that whenever people ask, is it this or this? If it's possible, it's usually both. Anything that can happen does. And so a lot of the people who are arguing about this might find that you can find evidence for both, all three mechanisms. Another aspect of this, now that we've covered the corona, I wanted to cover a little bit more about how the variations of the solar magnetic field happen. Dr. Guhathakurta yesterday talked about solar cycle 25, looking at it, outpacing the predictions. This is what was happening at solar minimum. This is us today. And this is what those coronal images, those high energy images look like over the course of a solar cycle. And so you have very little magnetic structure during solar minimum, and you have large sources of magnetic field here. And so you have very little magnetic structure during solar minimum. And as you go to solar maximum, you have these large active regions and sunspots, which are often at the root of active regions, at least before they diffuse. And you'll have coronal hole structures that appear in different locations. During solar minimum, typically we have coronal holes, or what we call open field lines, meaning that the field lines extend out far into the heliosphere and are a source of solar wind, only at the poles. But during solar maximum, we start to see these open field lines everywhere. Now, this is another wavelength of the sun provided by the Stereo Observatory. It is iron 15, which is 14 times iron. And I should say, in all cases, these are energetic wavelengths, extreme ultraviolet, which is somewhere between ultraviolet and X-rays. And so we have colored them, colored the images so you can see them just with regular visible light colors. All right. And again, the solar cycle itself varies, and the sun varies with the solar cycle and the heliosphere, and also the responses at the planets. But the solar cycle, in addition to these up, down of the solar cycle, this goes from 1750 to now. And if we go back a little bit farther with this, when sunspots first started getting to be observed, there was prolonged period of very little activity, and the sun does go through these times where and right now the sun is pretty active compared to its history, its recent history. We can use tree rings and ice cores and all sorts of isotopes to understand the long-term variation of the sun. And that is through what Dr. Guhathakurta talked about yesterday, how these cosmic ray fluxes, when the solar magnetic field is weaker, more of these particles are able to penetrate the heliosphere. And so we will have so we can infer even farther back through millennia the variation of the sun's activity. And there are periods of stronger solar cycle, and there's periods of not much going on. And so there's always a fun debate happening in our field. What's going to happen next solar cycle? It's a big question. And you can see this prediction right here. And you can also see that 25 is really, really exceeding solar cycle 25, the 25th solar cycle that we've charted is exceeding our expectations. All right. So going out from the corona, we have coronagraphs. You saw some of these yesterday. Coronagraphs block the view of the sun, and so you'll have a image of the sun, and then coronagraphs, because we have to reject roughly Some coronagraphs are so sensitive, they keep they reject 1 billion photons for every one they keep. They're very sensitive instruments. And so by blocking the sun, we can see the solar atmosphere. What they are is they're an artificial eclipse. Solar eclipses can show the extended atmosphere of the sun. And so what we see now is the solar structure moves outward. We can see this extending outward, and then look at these long structures. This, you can see there's lots of structures that extend out there, and this forms the base of the heliosphere. Some of these flows are fast, some of these are slow. And so this forms the base of the heliosphere and the structure that moves out there. So some of these structures are what we call helmet streamers or streamers. Those are complete loops that when they're stretched out, the magnetic field goes out in here. And when the magnetic field is stretched, it causes a current sheet. So you have opposing magnetic field. And if you're familiar with Maxwell's equations, you know that if del dot B cannot be 0, and the closer it gets, the more current there will be between the two. And so this moves outward to become these streamer structures. And they're also the source of what we call heliospheric current sheets. During solar minimum, we can sometimes call it the heliospheric current sheet, but when there's a lot of variations and there's a lot of streamers, we observe current sheets with a much more complex structure. There's also very cool things called pseudo streamers. Now we're going to get into finally something, and I will talk about this a little later, something that's not outside of your textbook. Your textbook really had this classic stuff, but we're starting to understand better the roles of the structures that are determined not just by these classical shapes, but these converging lines that have the same polarity. They're called pseudo streamers because they behave a bit like streamers, but they don't have a current sheet in them. And so they are not so easily identified out in the far heliosphere, but they are playing a role in determining the structure and processes in the corona. So hang on. I hope you guys don't mind. I'll get back to that in a little bit. There's a phenomenal paper by Matthew Owens. I highly recommend it. Just on a lot of the basics of solar structure and turning into the solar wind. And so we start from these coronal magnetic structures, and when you expand them outward, the sun is rotating. It rotates once every 27 days. Now, the typical time that it takes something from here in the solar wind to propagate to Earth is about 3 to 5 days. And the solar rotation is 27 days. And so this thing, the sun can turn 30 to 45 degrees in rotation between when that solar wind source leaves and when it arrives at Earth, and farther out into the other planets. And so this solar rotation combined with the solar wind moving outward forms what we call the Parker spiral. And that is named after Eugene Parker. Parker Solar Probe is named after him. He is the person who really refined the theory of why the solar wind is possible. It was predicted by scientists before that, or at least somewhat described, but Parker's theory is the one that explains how the pressure of the inner as it moves out accelerates the plasma as it moves outward and forms the solar wind. Now, the interesting structure is, so if we have, let's say that we have a negative magnetic field coming out here from, let's say that there's a negative polarity coronal hole, meaning that most of the field lines that are coming out of it are pointing towards the sun. So you have this, and then here we have some sources of coronal of solar wind that is positive polarity. And like we said earlier, the boundaries between these polarities, we have current sheets. And now it rotates. And then when it rotates, you start to get this structure where the current sheet, because this is not perfectly homogeneous, you start to get these things called, you start to get this full current sheet that expands out into the solar wind. It's complicated, it's interesting, and there's just so much. The models really try to predict what's happening here, looking at these magnetic field, and predict what's coming out here. Man, I just they do a pretty good job, but there's definitely more work to be done. So if you're working on that for your graduate thesis, it's a great topic. So we
Hey,
have this.
Barbara, can we,
Oh, yes,
yeah, can
yes.
we just go back to that picture? I just wanted to emphasize, I think there's some back and forth in chatting about
Okay.
how at solar minimum, the coronal magnetic fields are draping down over the current sheet. And just wanted to emphasize that. And so that's a good picture that I was trying to like post in chat.
Yes.
But
Yes, thank you. Yeah. And so and this is not, again, this is by no means simple. I'm trying to give you a good again, the textbook does a wonderful job getting into this. And I can see I'm already at 40 minutes after the hour. Okay. So I hope it's okay if I mean, I guess Nick and Mark will yell at me if I take too long. And so let's talk about these solar wind features. Now, solar wind speed depends on coronal features and the solar cycle. And so, like I said earlier, if you have a coronal hole, you can have a fast solar wind. So this is a complicated plot, but it's very useful. What it's showing is the farther out it is from the sun, this scale is the speed, whereas the color is the magnetic direction. And so red means it's pointing outward and blue means it's pointing inward. This is near solar minimum. This is 1996. And so this image is a composite of an inner image and a coronal image. And Ulysses is a mission that went over the poles of the sun. It had a very inclined orbit. And so these are measurements from that mission. Now, this is misleading a bit because it took over a year for Ulysses to make all of these measurements. Ulysses has a very long period. And so when it was, so it took a long time for Ulysses to collect this data, whereas this is just a single image. And so don't think that we just got a snapshot. It took a lot of time to build that up. But so you can see that there are fast wind observed at Ulysses. At Ulysses far out there, this was 1,000 kilometers per, no, it's 750 kilometers per second. Whereas as you are going more towards the equator of the Earth, where almost all of our observations are from, they're really from the ecliptic plane, the solar wind is much, much slower. And it's also more mixed polarity because that is location of that current sheet. And that's where we're getting these transitions that that are so interesting to study. Ulysses' second orbit went around and this was near solar maximum. And all the structure was changed. On Ulysses' third orbit, like I said before, the solar cycle, some people call 11 years-ish, some people call it 22 years-ish, because now when we went towards solar minimum again, the magnetic structure of the sun was such that the positive polarity or the outward IM magnetic field was coming from the southern pole of the sun, and the inward polarity was coming from the northern pole of the sun. So we have this variation. It's taken a lot of years and a lot of effort to understand how these structures on the sun become the solar wind. And we're not done at all. In situ measurements challenge us to understand large scale and small scale structure together. So this is what it looks like when you look at the solar wind near Earth. This is the velocity. And so we have a velocity near Earth, and it's about, it's going, this black line it's a little less than 500 kilometers per second until we get to the current sheet, and then we get to a higher velocity or a higher solar wind speed region. That's about 700 kilometers per second. And this density, the red, shows you that when there is high speed wind chasing a low speed wind, you get a ramp up of density. That's how shocks can form. That's how a lot of energetic particles can form. And so even when you've got basic structure and you're just sitting there passively collecting it, you can see variations in magnetic field. Here's that abundance that we were talking about, heavier oxygen and heavier carbon. The ratio that's not heavier. It's the ionization. You can see that there are different, these ratios change through different regions of the heliosphere. Now that's just for the solar structure. The reason this is varying is because it's the heliosphere is rotating, and the solar wind is sweeping past Earth. But whenever you start to have an eruption, look at the size of that thing. A coronal mass ejection can be huge. And it can cause, and that is also very observable when you get out into the heliosphere. You can measure its magnetic field, very large. The velocity, you can get a large pickup in velocity, and you can get a shock, and you'll get, and this is another source of those energetic particles that you guys will be learning about tomorrow. All right, sorry about this. And so these large scale coronal variations that result in the large scale variations of the heliosphere. So the rotation, you get these different air, you get the slow speed wind, the fast wind moves into and compresses the slow speed wind, and then you get these structures that you can observe out in the heliosphere. And so I've tried to give you a quick, just sort of a summary of the processes, and it's explained beautifully in these heliophysics textbooks. They're really unprecedented when it comes to the quality. The textbooks were authored by many great heliophysics scientists, including some of your faculty on this summer school. But this one was written, I think, in 2008, 2009. Has anything happened since then? The short answer is yes. The longer answer is yes, yes, yes. All right. Couple things, important things happened for coronal and heliospheric physics. There were the launch of the Solar Dynamics Observatory. I've been showing you images from that. But what's really exciting lately is the launch of two missions: Parker Solar Probe, which is going closer to the sun than far closer than any spacecraft has gone before, with both images and sensors to detect the magnetic field, the density, the velocity. And Solar Orbiter. Now, we talked about Ulysses going over the pole and measuring the solar wind velocity and magnetic field, but it did not have imagers. And so we weren't able to image and see what was happening at the high latitudes of the sun. We just had images from near the equator or the ecliptic plane of the sun. Solar Orbiter is giving us a view outside the ecliptic, and it also has a close approach to the sun. It's within a third of an AU of the sun, and Parker. So the combination of these two is changing a lot of what we understand about how the corona turns into the solar wind. So let me, you guys can just tell me when I'm going too long, but so to understand the source of the solar wind, we have decades of observations, both in situ, meaning that the direct sensing of the plasma and measuring magnetic field density, things like that, and remote sensing, meaning that we're taking images, collecting photons, and doing something creative with photons. And that has allowed us to examine how the corona evolves into the heliosphere. But there are still some basic questions. How do the structures in the inner corona supply the solar wind? And what processes govern the transition from the corona into the heliosphere? Can we define what is the outer limit of the corona and the inner boundary of the heliosphere? So we know the solar magnetic field is complex. I show you these images, there's all sorts of interesting stuff happening. But if you like Dr. Guhat Kurta was showing yesterday, and I will show you just a single image from a coronagraph. Now this is the size of the sun, and it goes out very far. This is, I think, a sixth of the distance to would be the sixth of the distance to 1 AU, or the what would be the distance to Earth. And you see this thing now, it looks quite, these streamers are here, like we were talking about before, and it looks very calm. When there's not any eruption, the solar wind looks pretty nice and quiet. These are planets here, these are stars. So it looks like the outer corona is more calm, and on the interior, there's a lot more structure. There's a transition, it seems. So so what do we expect when we get to 1 AU after all this calmness goes to 1 AU? You already have seen some of this, but even when there's not a large structure, even when there's still a lot of variations. And you can see, like, these are real. This isn't noisy data. Like all of these small scale structures, magnetic field, velocity, and density there's a lot of small scale as well as large scale structure in the solar wind. It has shown us that there's tremendous and it requires a complex explanation. Another good job you can have, turbulence. You can do that a long time. That's a steady job. I would say though I think I do CMEs, and I think CMEs are fun, because you can go to a conference and you can hear someone stand up after a talk and say, look, whatever you were talking about is totally wrong, and I also published that 20 years ago. CME people are the worst at that. And so, and so they're all good topics. Anyway, so what's
10:50 warning, so we're really
all right,
out of time.
So all right, let's I'll skip through these really quick. So the story is, the corona is ever varying. There are good studies that have shown that if you look at this, even these seemingly slowly varying structures, there's a signal and there's a lot of flows. And the answer is, it just depends on how you look at it. This is reprocessed data, and this is what a coronagraph looks like when you've reprocessed the data. The punch mission will do this very well, even better. And that's why the punch mission is being launched, is to understand these small scale processes, and everywhere. It's not just during one part of the corona. There's interesting stuff happening everywhere. So we used to think that the inner corona, you'd see it be complex, and then outer, maybe it's kind of simple, and then at some point it turbulence or something causes it to make this complex structure. But as it turns out, it's complex to complex to complex. And again, then so even the supply of the solar wind is complex, and with turbulent processes, it's even harder. And because this is what the solar wind looks like, all of these variations, all this density, the simple question of where does this corona turn into solar wind stops being a question of what the surface is. And so we used to say that it's when the solar wind is no longer able to have a magnetic signal back to Earth. It exceeds the magnetosonic speed. So once it's faster than that speed, signals cannot get back to the sun, and we call it open. But it looks like there's an Alfvén zone. Another understanding the source of the solar wind, those little nanoflares I was showing you, those things, it turns out that these small scale reversals and these small scale structures and reconfigurations appear to be happening. Parker probe found them, and solar orbiters finding them far into the sun. They are a feature, they're a common feature, there's quasi-ubiquitous, and they are a part of the solar wind. So you're not just getting straight field lines, you're getting interesting magnetic structures happening. Finally, another aspect of the source of the solar wind, the Parker model talks about the steady flow of solar wind from the sun, but the answer is not fully there. What starts that flow? What supplies that flow? Parker explains that when you have a flow, then it will accelerate away from the sun, and then eventually it will become supersonic. There's now a lot of evidence that from these new missions, including Solar Orbiter, which goes over the poles and sees as well as senses these things, that there's small scale jetting activity that looks like it is a major part of what supplies the solar wind. And so there's a lot of important science to come. I only really went out to about, this is not to scale. The heliosphere again is about, it goes out to 100 AU. And so, but this is from the Shield Drive Center. The solar wind gets even more interesting and weird the farther out you get. And there's a lot of missions and images working on that. So I'm just gonna plead the fifth, because I don't have enough time, and invite you to the Shield webinars are online. They get excellent speakers, and the Shield Center is a group of people that are dedicated to really understand how the entire heliosphere evolves and what it's and how it varies. So please join us on Helionauts if you haven't. I would love it if everybody here, you can see solar wind, solar surface, solar flare data sets. I know this is small. Flow tracking for the punch mission. There's lots of interesting topics that are here and if you join in, you can join the conversation and contribute and ask questions. Anyway, so that's it. Sorry I took a little longer, but
Thank you very
guys gave
much.
me a hard topic. Guys gave me a
In a short time. So, since we're running late, if you want to ask a question, please do allow one. We've been having a bunch of questions in the chat, and then if you're able to stay on, we'll do that. But any questions, if you could raise your hand. Okay, so go ahead, Kataki.
Hi, thanks for the nice talk. I wanted to ask about the streamers. So where do you see the source of the streamers on the surface of the sun or in the EUV images? Yeah.
Yeah, so let's go back here. So it is a little, it's a little subtle. If you watch this thing here, streamers are large scale structures. Now, active regions are small scale. You can see the loops and things like that. Streamers are a function of a lot more of the magnetic field of the sun. And so a typical width of a streamer is maybe 30 degrees or something. And so the base of the streamer starts at, at one latitude and then ends at another latitude. And so it is, you take some experience and usually a model to predict from looking at the photosphere and the magnetic field where the streamers will appear, because the streamers are not just a function of this small scale stuff. It is the function of the entire corona and how it connects to itself. And so it's not super simple. But what may help you a little bit is if you look for magnetic field extrapolations of the sun, where you can see the sun, it's the solar structure itself, and then you can look for the magnetic model that takes the photospheric magnetic field and predicts what the magnetic structure is, and then you can start to see how it evolves into that. But it's subtle. It's and sometimes the models are wrong.
Great.
Is that okay? Ask me an easy one,
Thank
somebody.
you.
Yeah. So just one last question. If it's short, we'd like to stop at the hour, and and we'll start Enrico at 10 after. But Ravina.
Yeah, hi. Actually, my question is, so we see that the solar irradiance varies like from solar minima to maxima, like especially in the extreme ultraviolet, the difference is a lot. So does that mean, like, what is the reason behind it? Is it because of the electron density which increases and then collisions dominate, collisional excitation dominates? So
Yeah. So this is a good example. Solar irradiance is a fascinating study because you don't just do that to understand the sun's energy output. You also do it to understand the energetic input to planets. And the Earth's ionosphere is very strongly dominated by solar radiance processes. You're correct, Ravina, that the EUV and X-ray are the largest magnitude of variation. The solar photosphere does have a variation with solar cycle. It does. But it's a very small fraction. The more energetic, the larger the variations. EUV can have variations of whole factors, and X-rays can vary by orders of magnitude. And so the reason that there is so much variation is, again, it's the magnetic field. The magnetic field is the reason for everything. And so this looks quiet because there are no energetic magnetic active regions here. And so we call this quiet sun. And the solar structure is relatively simple. So the solar structure there looks kind of like this, where you just have a strong polar flux, whereas during solar maximum, it looks like this. And so, again, the photosphere, the total flux from the sun does vary, but not a lot, small fraction of a %. But it's the energetic wavelengths that vary greatly, and that is what those are the ones that drive the dramatic changes, especially in the Earth's ionosphere and also at some planets. So yeah, and I'm sorry I didn't get much into irradiance. I have a fun talk just on solar variation timescales, and I go into a lot of irradiance there. But you guys gave me solar wind too, so
Great. Well, thank you very much,
Thank you.
Barbara.
great.
And Nick, we'll take a short 10-minute break, come back at 11:10 Eastern time, US.
That sounds fine to me. And Barbara, you're going to be available in an hour for office hours? Did you leave?
Yeah.
Okay,
So
great.
yeah, and I think I should be able to stick around most of the day.
Oh, great. Okay.
Great.
The first meeting is in 2 hours, so.
Okay.
Thank you very much. So Enrico will be starting at 10 after the hour. And so grab another cup of coffee, breakfast, lunch, or dinner, wherever you are. And we'll see you in 10 minutes.
Okay, today I would like to introduce you to how the sun looks like in several different wavelength ranges. Most importantly, you can observe the sun in a lot of many different ways with different instruments. The most important being spectrometers, which allow you to record spectra, and imagers, which allow you to record some images of the sun. I will discuss the latter, imagers, and in particular, I will take the AIA instrument on board of the Solar Dynamic Observatory as an example to see what we can see really with data in the very different wavelengths. And in order to do that,
Enrico, can I interrupt for a second? We're not seeing or at least I'm not in your full screen view. We're seeing it in the sort of editing mode. Yeah.
Okay, so you can see nothing, right?
Well, we can see the slides, but we also see the slide sorter on the side and the editor panel on the right.
Yeah, because apparently I cannot play this thing. Okay, let me see. Can you see that now?
Oh, that's great. That's perfect.
Okay. Okay. So I will be using the AIA instrument on board of the Solar Dynamic Observatory as an example. And in order to understand how to use what we see with this instrument, I will first describe how the main components of an imaging instrument and why they're made the way they are made, so that we can understand what the images look like and why they look like they do. And then I will just review how an observation done almost simultaneously by this instrument across all the wavelength ranges. And then eventually I will discuss a little bit how to use this data with some diagnostic techniques. So first of all, what are the main components of an imaging instrument? And there are several components which are all equally important, but the ones I would like to stress today are the aperture, the mirror system, and the detector. Now, what are they? The aperture is, like the word says, basically the aperture of the telescope. It's where the sun, the light of the sun gets inside the instrument. And it has two main roles. By its sheer size, it demands the amount of incoming light inside the instrument. But most importantly, through the use of filters, in the aperture, you are rejecting all the light that you don't want to see. You're not rejecting all of it, but you reject most of it. If you want to observe the solar atmosphere, mostly it emits an extreme ultraviolet X-rays, and the light from the photosphere, which is in the visible and in the infrared, basically they are not good for you because they don't tell you anything about the atmosphere, but they carry a lot of energy, and so they can heat the instrument a lot. And so you use the aperture and the filter in the aperture to reject it. Then once the light gets in, at least the light that you let inside the instrument, the mirror system is the thing that the light encounters. This can be done with really mirrors or lenses in all the instruments or in other type of instruments. But essentially, the mirror system has also two different objectives. First of all, it has to build the image of the sun into the focal plane where you put eventually the detector. And so it needs to be done as good as you can in order to have a nice image. And second, through the coating that you put on the mirror surface, the instrument selects the real bandpass that you're interested in. While the aperture, the filter in the aperture rejects a lot of light, it lets in big chunks of the electromagnetic spectrum. Anyway, it is at the mirror where you do the selection, the final selection, and we will see some examples later. And then once the mirror focuses the image in its focal plane, then you put the detector there, and the detector has the role of record the radiation into an array of pixels, and then transmit this array of pixels into the electronics where it gets processed and then sent back to Earth. So these are the three main components that I would like to discuss in more detail today to understand what this type of images, like this one, what they really mean. What are you observing really in these images once you record them, and how can you use this emission to measure something? So, and by the way, if you have any questions, you can interrupt me, but I cannot see your anything in the chat, so just please do interrupt me. Anyway, so for the mirror system, let's focus on that in the first place. The goal is to produce an image with as little aberration as possible, meaning the best possible image you can record. And also it needs to be compact because you don't want to send into space a huge instrument. It can be light because there are mass constraints and noise emissions, and sturdy in order to survive all vibrations during launch. And there are several different types of mirror assemblies, some of which are shown in this slide. The first one is really the one of the instrument that we'll be talking about most, which is the AIA instrument. And this assembly is the Cassegrain telescope. It has two mirrors, which both work with the surface of the mirror being almost perpendicular to the direction of the incoming light. These are so-called normal incidence mirrors. And there are two of them. The first one, the primary, is a parabolic shape, and the second one is a hyperbolic shape. And the focal plane is just behind the primary mirror, so that the design is fairly compact. Another one is the Richer-Chrétien telescope, and this has been used for the solid stereo imagers. And this again has two mirrors, and the focal plane is just behind the primary mirror, and both of them are hyperbolic. They have different characteristics, different limitations, but these are the designs that have been used. And these work mostly in the extreme ultraviolet wavelength range. If you want to go into the X-rays, and we will briefly hint at some X-ray observations today, you need to go into graded incidence because normal incidence doesn't really have very much reflectivity. And so you have several different types of design. The most popular of which is the Boulder telescope. There are 3 versions of them, where again, there are 2 mirrors, both of which work with the radiation coming with a very shallow angle relative to the surface of the mirror to enhance reflectivity. There are several combinations, hyperboloid, paraboloid, and again, the same band switch between primary and secondary. And in one case, the Boulder 3, which is fairly popular, is actually uses also an ellipsis. But most importantly, all these need to be compact, light, and sturdy. And it is in these mirrors that you go through coating them before launch that you create the real selection of the final wavelength range you're going to observe. Now, how do you select the wavelength range? The first big selection is done at the entrance filter, the one whose main job is to reject light. And here is an example of the transmissivity of an aperture filter made of aluminum. And you can see that it goes from basically the hard X-rays, 1 angstrom or so, all the way to 1200 angstroms. And since these are used for extreme ultraviolet instruments working on this range, they need to be as high as possible and as constant as possible in this range. The transmissivity needs to be as high as possible. And it works very good between 170 and, I would say, 800 angstroms. Unfortunately, there is a big hole in the soft X-rays where the transmissivity decreases dramatically. But what's most important here is the huge decrease in the transmissivity at longer wavelengths. This is what keeps the bulk of the energy emitted by the sun away from your instrument. Then, for this part of the radiation that gets in, you enter in you hit the mirror, and you coat the mirror in such a way that basically the reflectivity of the mirror gets restricted to an extremely narrow wavelength range. This is an example for the AIA instrument on SDO, where you have all the coronal channels, 94, 131, and so on and so forth. And you can see that this is the reflectivity of both the mirrors combined. And it is peaking at a very precise wavelength, and it is very narrow. In this way, there are 7 of these mirrors, essentially, these coatings in different parts of several different telescopes in this instrument. Each of these lets only pass a radiation in a very narrow wavelength range. And we will see in a second why. The longer the wavelength, the broader is the bandpass that gets transmitted, and unfortunately, the lower is the reflectivity. So, in a sense, even if I have a very large entrance aperture, really the effective area, which is contributing to the images that I see, is actually a lot smaller. And then you have this the detector, which in itself introduces some wavelength discrimination, because it can be sensitive more to some wavelengths instead of others. And altogether, these 3 filters define what we call the effective area. And the effective area is the surface, an imaginary surface that collects, it's an imaginary aperture surface of an instrument which is perfect and lets 100% of the light be recorded. And from an instrument that say have 40 centimeters square of surface, the effective area can be as small as 1 centimeter square. But anyway, this is how you select the wavelength and you determine the sensitivity of the instrument. Question is, why do we care about being so narrow in our selection? So let's look at this. Let's say, for example, let's take a couple of the AIA channels as an example. On the left column, you have the 94 angstrom channel, and on the right one, you have the 131 channel. The black spectrum here is the spectrum observed from a star by the Chandra Observatory. I just chose this because I had the figure handy. And the red one is a simulated spectrum. But what is important on the top row is this Gaussian-looking curve. This is the effective area, which basically weighs all the spectrum which is reaching the instrument, the mirror, and weighs it privileging the emission at the peak of this curve and killing all the other. So that eventually on the bottom row, you see what radiation the detector actually sees. And this radiation is focused on this case for the 94 channel on a spectral line of iron 10. There is something else, some other contribution here, but the bulk is iron 10. And for the 131, it focuses a lot on iron 8, which is a kind of a colder iron. And there is some contribution still from iron 10 and oxygen 6. For example, neon 8, which would be fairly strong, neon 7, sorry, which would be fairly stronger, then this gets penalized. And anything, say, beyond 134 or shorter than 126 simply doesn't reach the detector. Now, why do we care about selecting a particular ion over others? Well, look at this. This is, as a function of temperature on the X, the fraction of all the available atoms of iron, which are ionized at a certain way, in a certain way. One means neutral. This is first 1 time ionized, 2 time ionized, another way 8 time ionized, 16, 24, and bare nuclei. And each of these has a peak as a temperature where the ion is the most abundant of them all. So if I see a line, say, of iron 10, for example, which is this guy down here, I know that this line is formed in a very narrow temperature range. And this is why we want to focus in an imager on a wavelength range, which is very narrow, so that I can let in as few lines as possible, so that the plasma that I'm really seeing, the plasma that emits the radiation that reaches the detector, that plasma I know that is formed in a very narrow wavelength range. So this is why we want the imagers done in this way. What are the pros and the cons of filtering the spectrum? First of all, you improve, like we said, temperature resolution over instruments that let in a lot more lines and a much broader wavelength range. And by stacking one image after the other, I can create a movie of the temperature at a certain limited temperature range. And also, as you see, a spectrum spreads all the emission, say, in a spectral line in several pixels. And so each pixel has less radiation. By summing everything, even if it is weighted, I'm increasing the signal to noise. And so these instruments tend to be relatively bright. Problems are, there can be contamination from other temperatures. You have seen in the previous slide that in the 131 channel, I have iron 8, but also I have neon 7, oxygen 6, and iron 10. So I have multiple temperatures which kind of overlap and contribute. But also, I can have in the same wavelength range multiple ions formed at different temperature available. Look at this. This is again a spectrum from the Chandra Observatory. Doesn't really show very much because the source was relatively faint. And this is the iron 8 doublet that we were discussing. So, and this is during a quiescent phase of a star. But if the star starts flaring, the spectrum changes completely. Iron 8 gets ionized away, and ions are formed iron 21, 22, and 23. Now, iron 8 is formed at around 800,000 Kelvin, upper transition region, no more than that. These ions are emitted in a flare, and they are emitted in the same wavelength range. So if the 131 channel, for example, was built knowing that outside activity, you would see coldish plasmas. During flares, you had a real flash of very hot plasma. And these, let's call them dual channels because they can see, well, they're optimized for multiple temperature ranges at the same time. So how do I choose the wavelengths to select for when I build my instruments? Well, first of all, I need to know what I want to look at, what type of physics I want to look at. Do I want to see the quiescent everyday quiet sun, or do you want to see flares, active regions, and all these activity events? Do you want to observe also the disk, or are you interested only on off-limb instruments, observations? Then once you choose, say, for example, I want quiescent, so I can see the extreme ultraviolet, or I want activity, better going to the X-rays or some other type of extreme ultraviolet. I need to pick the right wavelength range. Normally, activity suggests X-rays because radiation there is formed by ions which go from iron 17 up, so something which is formed beyond 5 million degrees mostly. Quiescence is better in the extreme ultraviolet because you have a lot of ions formed at very different temperature ranges, so that they can span the entire solar atmosphere, and they can really pick the one that they prefer. And if we want to see really colder stuff, I have several options: extreme ultraviolet, or so. This is, for example, an image taken on a carbon-3 transition, which is formed below 100,000 Kelvin, for example. Once I select the wavelength range, let's say I want to look at in the extreme ultraviolet, I have to pick the spectral lines. For example, this is a spectrum between 185 and 200 angstroms in the extreme ultraviolet, so observed by the ISO spectrometer. And you have several lines in this spectrum. Which one I would I like to observe? First of all, I want them to be bright. It doesn't make any sense to build an instrument to look at these little lines, which would provide very little counts. But then, if I say focus myself on blended lines or regions where I have a lot of lines, I may have a lot of confusion. I would like to focus on isolated lines so that I can reasonably be sure that what I see really is emitted mostly by this line. It never happens completely because you do have the width of the channel, which includes anyway several ions. But at least if I focus on a bright and isolated line, I can hope to minimize these contributions. Or I can say, okay, I might choose dual channels. I can do that on purpose. Okay, here I have 195, but on 192, I have an extremely strong flare lines, an iron 24 line. So, okay, I build a filter essentially in the middle so that I can see both of them, especially when a flare occurs. So this is how we make choices. And then with this dual channel, again, going back to the 131, at 1 million degrees or even less, you have this, the spectrum is dominated by these two iron 8 transitions. At 10 million degrees, you have these very big lines from iron 21 to 23, one order of magnitude higher in temperature than the usual quiet sun. So once said that, let's look at how the sun looks like as observed by this instrument. Now, this is an image in the visible light of the solar disk. So here you're seeing the photosphere, and you see that there is not very much going on here except the sunspots, which are darker. Now, this emission is a black body radiation, short of 6,000 Kelvin, is 5,770 Kelvin or something like that. And the sunspots are colder, not because, are darker, not because there is no emission. There is a lot of emission there as well, but they are colder plasma. And so since it is still a black body emission, the radiation is lower. And in this wavelength range, if you look at the disk, you cannot see the solar atmosphere, just simply because the disk is way too bright. Now, on the bottom left, you have a graph showing with the red the temperature of the solar atmosphere as a function of height, and in blue the density of the solar atmosphere as a function of height as well. Now here we're seeing really at the base of this plot, even below what is shown, it's really the base in a sense that what we could call not properly the surface of the sun. However, I can still see the solar atmosphere in the visible once I obscure the disk. Now, this is an emission taken from the COMP instrument, and this instrument can see, this is a ground-based instrument, so it can see the solar atmosphere every day, provided there are no clouds, just because it has a particular design which allows the instrument to block all the radiation from the disk. So, okay, you have then remaining radiation from the solar atmosphere. Now, you can see it in this way, and you have to block the disk radiation because this radiation is 1 million times brighter than the radiation from the atmosphere. And the radiation of the atmosphere is very interesting, however, in the visible, because it's made of can be made of two components: Thompson scattering of photospheric blackbody radiation, And the Thompson scattering is done by free electrons, basically scattering, bouncing the radiation coming from the photosphere from the original direction to your own line of sight. And even spectral lines emitted by the corona itself. And we will see later why these radiation can be actually fairly precious, to the point that new instrumentation like DKISS has been developed to observe this radiation also in the atmosphere as well. But in any case, this is what the sun looks like in the visible light, whether you see the disk or you block the disk and see the atmosphere. So with the same wavelength range, you can see very cold stuff in the photosphere or the solar corona at very high temperatures at around 1 million degrees. Let's see what happens in between and which wavelengths to use. And again, using the AIA spectrum, you can see the first thing. As you can see, the temperature at the beginning doesn't increase in the solar atmosphere, actually decreases to a minimum of around more or less 4,000 Kelvin. You can observe that at around 1,700 angstroms. And as you can see that there is really nothing beyond the surface, it's still very close to the surface. And there is some structuring here. You still see the presence of sunspots, but they're surrounded by places called plages, which are actually brighter than the surrounding sun. Outside of these regions, you have some structuring where you see small lanes, which seem to define some kind of web, if you like, some brighter points without a sunspot. And this radiation comes from mostly from the recombination continuum. There are spectral lines here as well, but the recombination continuum is by far strongest. And this is what is formed at these temperatures and heights. And it's very difficult to model. Then you proceed and you start to want to go up in the atmosphere itself. And already you hit a wall in temperature, the so-called transition region, which starts with the chromosphere up to, say, 50,000. Well, the limits of the chromosphere are not very well defined. And then goes into the transition region where the temperature jumps by 1 order of magnitude or more, and then into the corona. Here in this channel, we are observing the chromosphere formed at around 50,000 Kelvin, more or less. This is a line from singly ionized helium. It's the alpha line of the Lyman series, the Lyman alpha of helium-2. And it is at 304 angstroms. And this line dominates all the spectrum, all the nearby spectrum when you're looking at it in the disk. And you can see that this image almost builds up on the previous one. In the around, you don't see any more the sunspots, but where you had plages, where there are sunspots, you see a very large brightening. The chromosphere is a lot brighter in the actor regions, and these are the regions that we call actor regions because a lot more things happen there. And you see also in this little point without the sunspot, still you have a brighter emission. But also in the chromosphere, you continue to see this kind of small-scale structure in this kind of web that is encompassing the sun. And this is pretty much looking the same across the entire disk, except in these actor regions. Then you want to move up, and you really want to see what the transition region looks like. And here you encounter one of the dual channels. Now, there are two different regimes at work here. Outside of the actor region, you really are observing the material, a material which emits iron 8. And iron 8 is formed between 0.1 and 0.6 million Kelvin. Now, you remember that in the plots of the abundance of every ion as a function of temperature, the ion was present significantly anyway in a certain temperature range. This is why this channel has this temperature range. And this is the emission that you see outside of the actor region. You still keep a memory of this web of brightenings and which envelope darker areas. And this is what iron 8 looks like. And it's pretty much the same all across the disk. In actor region, instead, you switch gears. Iron 8 is present in some of these structures, which are actually magnetic pipes. And iron 8 is emitted by the coldest of them. But then all the regions, the very, very bright regions here in the middle, they're emitted by hotter plasma, emitted by other ions, much hotter ions. Then you want to move on, and you want to see higher temperatures. And then you just have to change the ion from iron 8 to iron 9. Now, iron 9 is actually has the electronic configuration of a noble gas, and so it is abundant for a larger temperature range. So it encompasses here both the upper transition region and part of the corona. This is why you see it's like having a dual channel in a single line, if you like, because you still see some of these web that we were seen at the other wavelength ranges. But then you still start to see more diffuse emission pretty much everywhere outside of the active regions. This is what the corona looks like, and we will see it in the channel. In the active region, I have a lot more of these magnetic structure called loops, which are emitted, which emit iron 9 radiation. And so I know that this radiation is from between 0.6 and 0.9 million Kelvin. Next, you really want to get rid of the transition region and look at the corona the way it was meant to be. And for this, you use yet another line, if it shows. Okay, you see more diffuse corona, population of colder active region loops. The next one is iron 12. Now, iron 12 is formed at 1.5 million degrees, and even in its breath, anyway, it's formed only in the corona. And now the image changes radically. This is hotter plasma. You get rid of the web of structures that cover the disk that we were seeing in the other channels, and we only see the much more diffuse radiation. This radiation is formed by an enormous amount of unresolved loops, which are closed magnetic field structure, host the plasma inside at this temperature that emit the quiet sun. Then you have the active regions, and the active region gets very bright, look a lot larger because now this ion is able to be emitted by pretty much all of the structures, the magnetic structures that are there in an active region. And then a new guy pops up, which are coronal holes. Now, coronal holes were barely visible or invisible in the previous temperature ranges. And this is why, and this is because in the previous wavelength ranges, the emission was emitted essentially by closed magnetic field structure, which were at pretty much overlying over the one over the other at different temperatures. Here, we are beginning to see an area where the magnetic field structures that emit the quiet sun are actually absent. These are the regions where the magnetic field is radial. Basically, it's not closed, but it is open into and goes into space, and where the solar wind is accelerated from, and that don't emit much less iron 12 because they are less dense, and so there is less emitting material. And most importantly, they are colder. And so these lines you see, these regions you see as holes in the sun, and you see them at the poles, especially during minimum, and also they can be scattered around in the disk. So you have the active region loops and dark coronal holes.
And Enrico,
yes.
a potentially quick question. It
Yes,
was noticed that the timestamp for the different wavelengths for AIA were slightly different. Is that due to different integration times for the different wavelengths, or are they sampled sequentially?
I think I'm not an expert in this instrument. I think they're sampled with slightly different exposure times because the sensitivity of each of these channels is different. But still, they are taken every 12 seconds. You have a new image, and so even if it is there are 1 or 2 seconds of difference between one and the other, they're almost co-temporal.
Thank you.
Any other question?
That's it for now.
Okay. So let's say I want to see even something hotter than this. And then I really go to another dual channel. This is the 335 angstrom channel, still of AIA. Now, this is another dual channel because in the outside of the active regions, I have a structured transition region which emits silicon 9, magnesium 8, iron 9 spectral lines. So you go back to seeing this kind of a small scale structuring scattered all across the disk, and the coronal holes can barely be seen. But when you hit an active region, the spectrum changes completely and is totally dominated by iron 14 and most importantly by iron 16, which emits one of the strongest lines in extreme ultraviolet. And these are really prime lines for active region physics. And then if I really want to see something hotter if outside players, I have to change instrument and go into the X-rays. And this is taken from XRT on Boulder. Now we have several hours of difference because this is what was available at the moment when I looked for these images. Still, you have these two active regions, and then you have some diffuse emission. Now, the filters for this instrument sample the X-rays, but a much broader wavelength range, so they include a lot of lines. Most importantly, you have mostly emission from hot plasmas, as mentioned to 23, which is what makes the bulk of the active region emission, and they are very, very bright. The fainter emission instead is emitted by coronal stuff from oxygen 7 and oxygen 8, 17 to 20 angstroms, which are kind of colder in the temperature of formation. And this is what makes the rest of the emission. And so this is how the sun looks like. But all of the emission that I've shown so far, actually it is formed only, it can be seen only very close to the surface, as if the atmosphere ended there. Why is that? Because all this emission is formed only by collisions. You have free electrons that collide with the ions, excite them to a higher energy level, and then the ion decays spontaneously, emitting radiation. However, if you do the math, you see that this emission depends on the square of the electron density. Now, if you look here, the electron density decreases very, very fast with height, so that the effective highs that you can see with these images stretches up to 1.5 solar radii at the very maximum. It's difficult to get anything farther than that. If you want to see further, the solar atmosphere, as Barbara showed, doesn't end there. It's a lot larger. If you still want to see it from afar with remote sensing, you have to change wavelength range. And now you use the white light. Why is that? First of all, you can do that in two ways. Either with ground-based instruments called coronagraphs, like the one I showed, or during eclipses. And the eclipses are by far the best way of looking at them for two reasons. First of all, we have a natural occulter of the moon, which happens to have the same diameter of the sun. So it occults the sun, albeit for a very short time, in a perfect way. And second, by occulting it, and since you are in the cone of the shadow of the moon, the dark gets immediately very dark. So you really have a very strong contrast between the emission of the corona and the background sky. And second, because you have two different processes that emit radiation, Thompson scattering and lines from coronal ions, but this time the excitation mechanism from this emission is different, and it's not anymore collisions. One is scattering, and the other is photo excitation, and both of them depend only on density, not on density squared. So their emission decreases much more slowly with height, and that's why you see structure all the way beyond 2 solar radii. And then you start to see these big funnels, which are magnetic field open structures along which the solar wind moves away. Or you see the closed structures for like streamers or pseudo streamers. You see all of them. Unfortunately, eclipses happens only once or twice a year if you're really lucky. So it's not really an extremely effective way of looking at the sun. LEO coronagraphs don't have these capabilities, but still provide another very good means of going farther than the space instrument or looking in the extreme ultraviolet. So, how can we use this data? The first and easiest way is what you're looking now. Unfortunately, now these two movies have different lengths, so they go out of sync right now after the first run. But anyway, you can make movies. Now, movies are not only beautiful to see like these ones, but allow you to do several things. First of all, they're great for activity events because you see them unfolding with this instrument with a 12-second cadence, which is incredible. Second, if you look at what happens when this filament erupts, a lot of things is falling down. Other things fall down and start to excite some reactions in other parts of the active region, which are actually far away from the eruption site, which then in turn triggers some other activity events. So you're beginning to make connection between different structures. And by looking at high cadence movies like this, you can make this causal connection between these different faraway structures. And then, of course, if you look, for example, to this active region here, which doesn't seem to be participating in this eruption, you see, anyway, the evolution of the morphology of the active region, how there are cold stuff. This is in 304, so this is chromosphere. Yeah, how there are these cold prominent stuff forming and becoming very bright during the very few minutes that this observation lasted, or this big prominence shedding material and changing the shape or so. So these are great way of looking at the sun. So the next things are they're quick and easy to make. You really need to have a good computer to do it. And they provide connection between distant structures. However, with these movies, except for timescales, you really cannot do any quantitative diagnostics. Next, you can build multi-temperature images. Now, what you do, you take images taken near simultaneously, even if there is a few seconds or 1 or 2 minutes of difference, and stack them one on top of the other with different colors. Here there is an example. With the blue, it's the iron 9 with a big coronal hole here. Green is 193, typical quiet temperatures. Red, active region temperatures. This is an iron 14 line. And what you see, coronal holes are seen in 171, and you see them in all their beauty. That the quiet sun in these regions here is a superposition of 171 bright points, these little things, and a more diffuse emission from 193. And then you have active regions, which mixes all channels. And interestingly, look at this active region. You have iron 9, the colder, visible at the foot points of found loops, which then evolve into iron 13. So they heat from 500,000 degrees, almost 1 million degrees to 1.5 million degrees. And then you have iron 12 showing other structures, and then you have iron 14 showing yet more structures. And then again, these are quick and easy. And then again, allow you to provide connection between different temperatures. Like, for example, in these fanning loops, or you can see that loops in iron 12 are not spatial with those in 211 and 171. And you can really start to do some more quantitative diagnostics. Although there are still limits to how much quantitative you can be. Then you have, if you really want to do, yes?
Just giving you a 10-minute warning.
Okay. Other things are temperature ratios. These are kind of old-fashioned. They were developed mostly during the trace era at the beginning of the 2000s. And I capitalized on the sensitivity, different temperature sensitivity of different channels. Hold on a second. Sorry about that. My dog was doing some damage. Okay, what you do, look at here what happens. You assume that the plasma is isothermal, and this is a big limitation. Now, on the top left here, you have the temperature response of two channels, 171 and 185. This tells you how much radiation I can see, how much sensitive is my instrument as a function of temperature. 171 is peaked on the iron 9, 195 is peaked on iron 12. And I know these functions because I built the instrument. On the top right, you have the ratio between these two. How much is the ratio in brightness, if you like, between these two channels is a function of temperature. Of course, as 800,000 Kelvin, I have little 195, large 171. I have a larger ratio, which then decreases as temperature is higher because iron 9 ionizes away, so this channel becomes less sensitive, and iron 95 gets formed, and so this channel is more sensitive. And I can predict that again because I built the instrument. Then you have the observed ratio. They isolated a loop here, and they measured the ratio along this loop. And this ratio, as you can see, changes between 1 to 4. This is the measured brightness ratio between these two images. There is some kind of variability, quite big variability, and this measurement has been done as a function of position along the loop from the foot point or near the foot point all the way to the top. And then you compare with this prediction. Now, this bottom right plot is just a boom of this bottom part of this curve. And this two dashed line showed the range of the measurement in this loop. And then even if I have almost a factor of 3 change in between this measured ratio, this translates in around 10% uncertainty in this loop. This is a quantitative measurement. Now, with these, you can do image ratios. You can really create temperature maps. and they're very easy and quick to do. However, and there are apparently very small uncertainties, even if I have a wild fluctuation in the measurement. There are two problems here. Normally, you have to assume that the plasma is isothermal, and this is hardly decayed in the solar atmosphere. So really, this gives you a rough indication. And also, if you look, you have these 1 million degrees values, but also you have another set of solution at around 300,000 Kelvin. Which one do I know? Which one is the right one? This is one of the limitations. And this is particularly bad. Okay, I was looking at the next region. I know it's very hot, so okay, I can choose this branch. But if I measure, say, a region in the 70, is it 500,000 or 700,000? It's quite a big uncertainty, which can make a difference in the models. So this is the second risk of this ratio or this methodology. Now, if you want to take into account the fact that the plasma of the sun is not isothermal, you can do a differential emission measure diagnostics. Now, this diagnostics measure the temperature distribution of the plasma, which is the amount of material as a function of temperature. So you assume that the plasma is optically thin, and this is a very good assumption in the corona, meaning that what I see on the line side is just the simple superposition of everything that I have. So I divide my line of sight in all the temperature range, possible temperature ranges, and the flux that I see beyond this quantity here, this constant, is done by two components. The emissivity of the plasma, how much the plasma at a certain temperature, the unit amount of the plasma at a certain temperature emits, and how much of this material I have in this temperature range. And I sum them over all possible little temperature ranges dt. Now, this is what I see in one channel. And I know the plasma emissivity because I can calculate the solar spectrum, and I know how my instrument reacts to the solar spectrum. So if I have several different of these channels, I can, knowing measuring F and measuring this plasma emissivity, I can sample this function here through an inversion methods. I'm not going into the details of these diagnostics. I'm just showing the results. I can determine this function as a function of the electron temperature, and this is what it looks like. From AIA, this is the image of a CME by Hann and Contar in 2013, I believe. And you can see in every single panel, you have a different temperature range. 0.5 to 1 million, you have an active region, you say the cold loops. You move hotter, you start to see the front of the eruption. And this front is brighter at 2 to 4 million degrees, while you're still seeing the rest of the active region, while outside of it, already at 2 million degrees, you have very little signal. So each of these panels is the amount of material at this temperature. Then you move hotter and you see the plasma, which is at smaller and smaller scale, which are the hotter one, until you go to at around 10 million degrees when you start to see the actual ejecta. This is probably reconnected material heated up to 8 all the way to almost 20 million degrees, more or less, where this material is what it gets ejected out of the sun. And since you do that using all the images of all the channels recorded almost at the same time, you can build movies of this. So the diagnostics here is extremely powerful. So you can make temperature distribution maps, you can measure time evolution, and you can do that for the entire sun even. What is the problem? Well, each of these filters samples several lines normally. Either there are dual channels, or even the channel with a single line is fairly broad. So this type of diagnostics is more limited in accuracy than if you use spectral lines. But still, it has a lot of power for utilizing temperature, by utilizing images and providing all the diagnostics at the same time. Then, since you have a lot of images done continuously as a function of time, because the extreme ultraviolet is observed from outside the atmosphere, so you're just standing at the sun 24/7, you have a big series of images. And now you do like they do for CAT scan, where they just rotate an instrument that sends a lot of X-rays around your head, and they collect an X-ray scan from every different line of sight, and then they rebuild the 3D map of your head. You do the same, but this time the instrument is still. What is rotating is the sun. And by utilizing a long series of images, you can reconstruct the 3D distribution of every single channel emission. And then you can apply all the previous diagnostics that I've discussed to 3D distribution of measured to every single voxel of the solar atmosphere. And you can determine temperatures, differential emission measure, densities. You can determine a lot of stuff. This is an example. Each of these plots is, on the left column is essentially density, on the right is temperature. And these are Carrington maps. There is longitude and latitude. So this is the entire solar, the entire sphere around the sun at 3 different heights, 1.025, 0.065, and 1.1 solar radii. And you really can then map what is the temperature. You see the corona holes, you see the streamers, you see local active regions, you see enhancements, you see a lot of stuff. Now, with this technique, you remove line of sight ambiguities, and it provides a formidable tool for local voxel level plasma diagnostics. And this is really unprecedented. However, the drawback is that you really need, in order to do the entire solar atmosphere, around 15 days of observations. And during these 15 days, the sun doesn't stay there frozen just for you to observe. It just evolves. So when you don't have very much of evolution, you don't have flares, you don't have coronal mass ejections, no new active region emerge. This method really provides very good reconstructions. During maximum, when you have a lot of activity, then you may have more problems. And also, it works best for the Western corona, and you need a high signal-to-noise ratio because, as you see, as you move out away from the solar surface, you have more and more of these points which are dark, meaning that the reconstruction failed because you didn't have enough counts. And now the last slide, the last of the diagnostic techniques, you can even measure densities in some cases. And you do that capitalizing that a different temperature spectra look different as seen by the instrument. And this that I'm going to say now can be done for CME ejecta. And this is because CME ejecta, especially the erupting prominence, gets heated to temperature where around a few 100,000 Kelvin. Now, these two columns are on the left, the 171 channel of AIA, and this one, the 193 one. On the top, you have the usual coronal spectrum, dominated by iron 9 for the 171, iron 12 for the 195, 193. And these are the filtered spectrum. But at lower temperature, the spectrum changes radically, and you have oxygen 5, this big line, and this big line dominating the entire both channels. And these two lines are density sensitive relative to each other. So you can use channel ratios to do plasma diagnostics. These are what this channel ratio look like as a function of the electron density. And between 5.3 and 5.5 in log T, you can actually measure the electron density, make density maps of the ejecta of CMEs. The pros, well, you have CME density distribution maps, and again, you can do time evolution of this density, which would be great for models. Cons, well, first of all, you need to be sure that you are in this temperature range, otherwise these ratios are actually flat. You need to remove the background and the foreground because these are emitting this spectrum, not this one. And the sensitivity of these ratios is below a factor of 2. That is not great, but it's still better than nothing. And so this ends my presentation, and I will be very happy to have questions.
Great, thank you. There was a couple questions in the chat. One was looking at was asking about using EUV data to do magnetic field observations, but really, if you're going to make a model, what would be the most important considerations or parameters?
Okay, for measuring the magnetic field, there are several techniques. You can go into the visible, and this is where the ground-based COMP and the latest and greatest decays, this is what they do. You measure polarization, and you measure changes in the polarization of the radiation. From there, you measure the magnetic field. You can do that in the ultraviolet as well, but you need a spectrometer. So you need to resolve a spectrometer, and there is one spectral line of all the spectrum emitted by iron 10, which is sensitive to the magnetic field. You measure this line and a few other iron 10 lines, and you can make measurements of the magnetic field. But unfortunately, this is the only chance you have for for measuring the magnetic field in the solar atmosphere. Then, okay, if you want the photospheric magnetic field, there are a lot of, you can do that again from the visible, and there are AIA, SDO, Hinode, solar orbiter, all these instruments have instruments that can measure this, the magnetic field in the photosphere. Now, for building models, that's a big question, depends what you mean. If you mean big global models, the first and most important input that you can give is the magnetic field. Normally, this is done by, as an input, the photospheric magnetic field. And from there, you build a magnetic skeleton, and then you, depending on the heating mechanism that you choose, you can build basically the thermodynamic of the corona and determine the electron density and temperature and all and the motions and the energetics and everything. And once you do that, you can predict what this synthetic corona would look like by utilizing atomic databases that let you calculate the emission of the plasma. So, what are the main ingredients? I would say the physics that you put in, the heating mechanism that you choose for heating the plasma, be it waves, the convection, or whatever, the boundary magnetic field, and that's pretty much all that it comes to my mind. These are the two main drivers, but
Great,
I'm not a
thank
model.
you. So, Ivan, go ahead.
Thank you, Enrico. Fabulous talk. I was quite interested in the density diagnostics using the DEM. So the images that we get from AAA are just two-dimensional projections on the line of sight. And I'm curious, is there a way to somehow find out whether there are density changes along the line of sight? So, for example, if we have a cavity inside the homogeneous medium or not, and can we use stereoscopic observations for that?
Yes, what we can do now is actually through tomography, because with that, you really result, it's like having AIA images, but for very small volumes all around the corona. And then you can use for every single one of these volumes the diagnostics that I described. So you can measure the density. Say you choose a line of sight, I'm going to look in the west limb. I can then, once I have a tomographic reconstruction, to know along this line of sight how much each of the channels has emitted, and then use that to measure the electron density. So you can do that. Signal to noise ratios and sensitivity limit these diagnostics to very low heights. I don't think that you can go beyond 1.2 and have really realistic results at the moment, but in principle you can do that.
Thank you.
Mohammed.
Hi, thank you. Great talk. So I was wondering if it's possible to get the temperature at specific wavelengths instead of the distribution of temperatures, or like practically, is it possible?
So you can measure the temperature using very limited temperature ranges if you have the right spectral lines. Now, we are going into spectroscopy here, which wasn't covered in this lecture. But if you happen to have lines either of different ions or lines from the same ion but form at different temperature ranges, you can use them to measure the electron temperature at that particular wavelength, a very, very narrow wavelength range. Again, you are including, for if you use different ions in the same approximation as the temperature diagnostics I named here for them, what it is, for the imagers, because say these are two spectral lines, say iron 9 and iron 12, the ratio will be very strongly dependent on the electron temperature. But again, you're making the assumption that they're both emitted by the same plasma, meaning that the plasma has one single temperature. If instead I have an entire line of sight, chances are that 171 is emitted here, 195 is emitted here, and we cannot do these diagnostics. And this is true for images and also for spectral lines. So in principle, yes, you can measure the temperature at specific wavelengths, but you need to be careful about what you're doing.
Great, thank you. I'm gonna hand it off to Nick for the rest of the day.
For the
Or rest of the day announcements before we break in office
Okay,
hours.
great. I'm in control now. Yeah, so I think we're moving into our sort of well, our office hours and meal breaks. So I'm not and Enrico and Barbara, I think we mentioned this in some of our communications, providing an opportunity for more informal discussion from people. There's at least one request for some open source code for some of the diagnostics. So and then if anybody's got any questions for either Barbara or Enrico to follow up on, or want to talk a little bit about your research, please with them, please feel free to do so now. Otherwise, we'll still plan to be back at 1. I think we still got 50 minutes for a meal break. And so between a little bit of office hours discussion and a meal break, that would be great. So if you've got questions, I think at this point in time, if you got questions for either Barbara or Enrico at this point in time, you can put your hand up and then unmute yourself and just ask your question out loud, and we go into a discussion. And you just Ivan, you just stay here. I'm now saying this is informal discussion, and have a meal break over the next 50 minutes. Does that work? Great.
And Enrico is one of the creators of Chianti, the code. So if you want to get any insights on that, he's the one to ask.
And is Chianti, what is the status of Chianti? Is it what language is it in? Is it open source?
Yeah, Chianti is freely distributed over the internet, either through SolarSoft, which is an ideal, but for those who use Python, they may want to either use the Python software that we have, or they can download their own version of the database and develop their own software to use it. But anyway, everything is free of charge, either through SolarSoft or through the Chianti website. And the status is that we just released Chianti, the 10.1 version of the database, which improves ionization and recombination, and also improves a few ions. And we're continuously basically updating it with better and better atomic physics, new ions, and looking at new direction where to provide new stuff. That's the advertising pitch for Chianti.
And Eduardo, I invite you to just unmute yourself and oh, is it? Never mind.
Yeah, and you should be able, I think it's at the bottom of the chat, if you click on ... you can save the chat.
As regular users, are you allowed to do that?
Oh, I'm not sure. Somebody, is there a save the chat option?
And it looks like Angelo has a question.
Yes, if I may ask about the density diagnostics for the CMEs that were mentioned. If I understood correctly, like from the physics of it, we can also use it to locate the shocks that are possibly formed around the CME, right?
Essentially, what you take the images, and by subtracting background around the CME ejecta, the colder stuff, the one at the center, you may be able to isolate the emission coming from those ejecta only. So you know where they are, and now if you know that the temperature is within that range, that emission is made by two different spectral lines, one for channel, and then you use a ratio between these two channels to determine the electron density. So in a sense, yes, you know at this point, if you're able to do that, where this emission comes from, and so you locate it, and you know what the density of this plasma is.
Yeah.
Let's see if I can show you something. Just give me a minute to pull up a paper.
Sure.
Where is it? Because I can show you what happens. Okay. Let me get to the image. Okay. Can I share my screen?
Please.
Okay, where is it? This one. Now, can you see this series of images? This is a paper on a CME ejector, and this is a channel from the UVI instrument on board stereo. And this is the 171 channel, which is nominally from iron 9. The CME starts here, this little thing, and you see it brighter, which means darker, because it is an absorption. This is prominence material, which blocks the line, absorbs the line behind it. And it's very cold because this is essentially neutral helium, neutral hydrogen. Then this thing gets spit out, disappears, meaning that the plasma that was absorbing here gets heated, gets ionized, so it cannot absorb anymore. And then it continues to move on until it appears, but this time it appears in emission. Now, from here to here, the plasma is heated, and by being heated, it starts to emit at different temperatures. So the spectrum is different. And here, chances are that this plasma is at the right temperature, and this emission is not done by iron 9 because it has not yet heated so much, but it is actually this oxygen 5 emission. And if you find the same thing also for the other channel, the 195, and you see a similar evolution, chances are that this ratio between this structure seen in this channel and the other channel, will allow you to give you some estimate of the density. And now you know that this density is coming from this thing, which is basically evolving slowly and making its way out of the field of view. Does it make sense?
Yes. I didn't understand the point where you said that in the first pictures that the plasma is heated so much that it cannot absorb any more radiation. Could you go on?
Here at the very beginning at 926 UT, you have really a prominence which is erupting. This prominence is cold. So it's mostly populated by neutral hydrogen, neutral helium, maybe a little helium plus. And all these ions are actually very good absorber at 171 angstroms. And so they block the radiation. Now, this is an inverse color image. So bright is actually dark, and dark like here is actually very bright. So this means that since this is brighter, in reality, in the real image, it is darker. And this is because this material is cold enough to absorb everything which is sitting behind it.
Okay, yes.
Then as this thing moves out, it also gets heated during the eruption. But being heated, hydrogen and helium gets ionized even further. And once the hydrogen is ionized, it loses the only electron it has. It cannot absorb anything. Same is for helium tube. Once it loses the only other electron.
I'm sorry, I kind of lost you. I cannot hear you.
We just lost Enrico. So hopefully he'll come back, but it might be a good transition. We can ask for this paper if it's been published and just submit that. But we're in office hours and break, so we could take an opportunity unless somebody had a general question that I can address, and I'm not sure if Barbara's back on yet.
I'm here.
Okay, so if anyone has questions for Barbara, and if not, I think Nick said we're going to return at the top of the hour.
That is correct, yes.
Okay. So have a good break and return at the top of the hour. And it's usually easier not to log off, just turn off your camera and mute. Okay, I see a question.
Okay, hi. It's just probably more like a general question. So I've been into a conference and I have heard about the project proposal called Firefly, which is like kind of like I think is proposed by New Ralphie at the Johns Hopkins about the which is the proposal of the multi-spacecraft that try to look at the EUV images of the whole sun. So I was wondering if anyone have like more information regarding that proposal. It's just like more like a general question. I don't know if like anyone have heard about it before or yeah.
I have not a Firefly with respect to EUV imaging of the sun. Okay. I don't know if Barbara.
To be perfectly honest, I am not super familiar.
Yeah,
I should be. Okay. I feel bad.
Yeah, there are other Firefly missions, but they're CubeSats looking at other atmospheric electricity and I think the other radiation, but we'll have to look that up.
Thank you.
Just don't wait for season 2 of Firefly.
Yeah. I feel bad because there's people on here in the building where I work that work on that, but I should really know more.
I am back. Sorry for disappearing, but
He's cursed. But I see, Ravina, thank you for a white paper on Firefly, but I don't know if there's additional information, but okay. So
getting back.
Okay, hi, Enrico. Yeah, we're going to take a break and come back at the top of the hour. Unless anyone has a specific question for Enrico, you can feel free to fire away. Ivan, I'm going to step away to be able to grab something to eat, but so feel free to unmute yourself in order of hand raise. So go ahead, Ivan.
Yeah, just quite the general questions about DM diagnostics. So it requires us to know the chemical composition model of abundance, of chemical abundance. So are there any currently established models of the coronal abundances, and what is the progress in that that's going on?
No. Abundance, talking about abundance, you open an entire worm of kind of worms, because let's say abundance of the solar atmosphere is not set in stone. First of all, because we know it very well, it's not very easy to measure. And second, because it changes depending on structure, depending on time, depending on the particular property of the plasma which you are observing. And the way it changes is not entirely understood, because we have a fairly good, well, there is a lot of debate, but a fairly good understanding and way of measuring the abundances of the photosphere. So let's take them for known, although that is not entirely true. The problem is that there is some process that changes the abundances of the sun from the photosphere into the solar atmosphere. One of the most promising model is called the ponderamotive force model. It's continuously under development, and new things have emerged recently, for example, which change how the values of the abundance in the corona of the several elements, depending, for example, on the type of waves that you have in the field, on the strength of the magnetic field. So it's not entirely clear. And normally, you have to assume more than know the abundances that you're using. So this introduces an uncertainty. Ideally, if you use then all the ions of the same element, you will have only a constant uncertainty. Basically, your DM may be shifted up or down in value by a constant factor at any temperature. Unfortunately, you normally don't have this privilege, and you try to use ions from the same type of elements, where the same types means elements which have the same first ionization potential. Normally, you try to use iron, magnesium, silicon. If you have it, maybe calcium, it's already risky, aluminum, again, risky. They're supposed to be changing from their abundance in the atmosphere is supposed to be changing from that in the photosphere in the same way. Although that is not entirely true as well, because the most recent development introduced nuances. So that is a big, big source of uncertainty in the DEM diagnostics. And if you do DEM from imagers, it's worse because you cannot see the lines, you only see the total. If you use spectral lines, you have the privilege of choosing, but again, you may have different elements, you may have to use different elements, and so the uncertainty remains.
Thank you so much. Could you just repeat the name of the current most developed model that you mentioned?
It's I'm writing it in the chat, because I'm not sure I'm pronouncing it well.
Oh, thanks.
Now, if you Google, if you go into the RDS and look for the publication of Martin Lemming, you will see that a lot of them are about this model. There is a leading review of solar physics, which is a good introduction, but then more nuances have been added as time goes on.
Great, thank you so much. It was really comprehensive.
Hello. So can I ask a question? So my question is again to Enrico. I'm again interested in density diagnostics. So I just wanted to ask, like, are there any comparison done between this method and other methods where we can get the densities? And if these comparisons are done, then what do you say about these comparisons? Like, do you see any discrepancies, or what do you say about it?
No comparison has been made because really this method has been introduced and by me and very seldom used. So really there is no comparison about that. Also because for that particular CME, there was some density estimate using spectral lines, but it wasn't really good because the line of sight was different, because the spectral lines were observed from by Hinode from the Earth, while the images were taken from stereo, which was, I don't remember, 20, 30 degrees away. So you really were not even sure you would see the same thing. So short answer, no, there is no comparison. Really. Actually, this is a very nice project, if you like, because it's really something that needs to be done.
Yes, because I actually work on radio densities, so electron densities, and I compared, like, right now I'm comparing that with the Parker Solar Probe observations, and then I see like a lot of discrepancy in that. So I was like wondering, like, if you see anything with this UV observations as well or not.
Okay, I'm not sure I understood the question because the audio came and went. I'm in a big storm here, so internet is not the best. Density. You're studying density, electron density of which structures?
Right now, I'm actually getting the radio densities from type 3 radio burst. So it's like radio diagnostics. Yes.
They may be emitted by different regions which are emitting the EUV spectral lines or images that you would use for the diagnostics. So I never worked on radio bursts, so I'm not really aware of comparison in the literature between these two different methodologies.
Yeah, so basically like
You hear
type 2 radio bursts are associated with fast electron beams and mostly the electron densities that we get from this thing. And now we are comparing that, like Parker's law probe is actually going very close to the sun, so we can actually compare the densities with that. So we wanted to actually validate the observation, because whatever we get with the radio is like it's remote observations, remote sensing observations. So that's why I was interested in, like, because EUV is also like remote sensing observations again. So I was just curious, like if we can see any difference in that or not.
I don't know, because again, what would be most useful to you is density diagnostics from the images, like I showed you, but there really is very little published about that. If you want to use spectral lines, that would be the best, because then you really can do diagnostics like it should be done. But there are very, very few observations, spectrally resolved observations of regions that can produce radio bursts. So I'm not aware of any, not only publication that has really done that type of validation, but whether there are observations that can be used. Honestly, I would have to go and look into it.
Okay.
The weak spot here.
Yeah.
Okay, hi. Hi, I have a question for Enrico. So I have like two kind of unrelated questions. The first one is about, have you worked with the instrument that looking at the, I think it's CDS and UVCS on Soho before? Because I'm trying to look into work on that, and I feels like I don't know where to start from that.
Okay, I never worked on UVCS, but I did work on CDS.
Okay.
Though my work of CDS stopped at some point because I became uninterested in the instrument, because after Soho was lost, the satellite was lost in space and then recovered, CDS suffered some damage. And so their spectra had a very weird line profile, but still it can be used. Now, the data can be found in the CDS archive, the Rutherford Upton Lab. And they're all there, and they're actually fairly nice in the sense that you can find them very easily, because they let you show, it's a user-friendly archive. And then in SonarSoft, you have all the software that you can use to reduce the data and then start utilizing the data.
Okay, thank you. And the other one is actually from one of the paper that you wrote about the carbon charge state ratio as the tracer for solar wind, as a tracer for solar wind source. Yeah. So I think in your paper you recommended that carbon charge ratio is a better proxy for the source region, or maybe like better word is like the freeze in temperature comparing to oxygen. I just want to know why do you think is that the case, and by how much would it be like, and how much better would it be? Like, would it like should be that, is it like 07, 06 still usable, or should we just using C6, C4 completely from now on?
Okay, there are two things which are important here. One is observational. Carbon in the solar wind is normally, I wouldn't say equally, but similarly divided between carbon 4, 5, and 6+. So you have a fairly good signal for all three of these ions. For oxygen, oxygen 6 by far dominates oxygen because of the way basically the wind is ionized. Oxygen mostly stops ionizing at oxygen 6, and only some leftovers are observed at oxygen 7+. So the signal is lower, but still you can see it. The other thing is that the oxygen ratio, actually the oxygen ionization, is sensitive to photoexcitation. And the reason is that, again, oxygen, basically both oxygen and carbon can be photoionized by the X-rays. But the wavelengths at which they are photoionized can be photoionized at different. Carbon can be photoionized all the way to from basically zero wavelength, hard X-rays, all the way, if I remember well, to 25 angstroms, something like that, 30 angstroms, while oxygen can only be photoionized from, what is it, 15 angstrom and down, or something like that. This means that carbon can be the X-ray spectrum is very highly dependent on the activity of the sun. It's mostly emitted by active regions. And so if you have more or less active region, you have more or less ionizing flux. And so the ionization of oxygen is affected. Carbon instead can be photoionized from 15 to 30 angstrom, which oxygen count. And there you have lines, spectral lines, very bright ones from oxygen and 8 and 7. And they are emitted by quieter plasma, so they're always there. So photoionization doesn't affect, it's the same at all activity levels for the sun. And so the carbon charge state ratios are a lot less sensitive to photoionization than the oxygen ones. To the point that from maximum to minimum, the value of the oxygen 7 to oxygen 6 ratio is the same in the fast wind at maximum as it is for the slow wind at minimum. So if you use some kind of proxy, say, okay, 0.1 above that is slow wind and below that is fast wind, you may be off because you are in the wrong period of activity of the sun, because photoionization changes them. If you heard the barking, that's my dog, unfortunately. And while for carbon, you don't have that sensitivity. It affects it, but a little bit, just not very much. And this is what makes carbon more attractive as a diagnostics than oxygen.
Okay. Oh yeah, that's very clear. Thank you very much, Enrico.
Yeah, most welcome.
My question is not really a question, but if Enrico could continue the answer from before, because I didn't hear it all. The connection was lost. About the density diagnostics on the CMEs.
Okay, essentially, I was asked whether there were density diagnostics from CMEs done with imagers and whether they had been validated against other diagnostics. And the diagnostics from which the validation was requested was from radio bursts, type 3 bursts, I believe, if I understood well. Now, the short answer is no, because, yeah?
You were showing some observations from the channel 171 from a paper, I think from 2010.
Yes, but I didn't do that diagnostics. I hadn't discovered that yet because I published this method in 2014. I never had the time to just took the images back and do the diagnostics. So that is still open, wide open for looking at it. But even then, it's difficult to compare it either to spectrally resolved diagnostics because the line of sight is different. We had spectra from eyes, from the Earth direction, but those were images from stereo, 20 degrees away. So it wasn't clear whether the regions were the same that you would observe. And as far as radio 3 bursts, I don't think there is any other data set for which we can do a direct comparison like this. But this is really something I'm not familiar with because I don't really know very much about radio bursts.
Okay, no, I think you confused it from the question from Ketaki. I was talking about the diagnostics, about the shock waves, if we can do it with the density diagnostics. But yeah, okay. Thank you.
Hi, Enrico, this is Ravina.
Hi.
So I want to know, like, I use Chianti to calculate the collision rates for UV spectral lines. So it takes into account the collision strength from Chianti as a function of temperature. So I want to know, like, how does it validate with the observation, or is it completely based on atomic physics?
Okay, the data themselves, they're all in their whole entirety calculated, because there are very, very few laboratory measurements of collision strengths and effective collision strengths or collision rates in general. So the database in itself is entirely theoretical. Now, there are ways of validating it if you take spectra for which you more or less know the structure of the sun that has emitted them, so that you can predict them reliably, and then you compare the spectral lines with observations. And we have carried out over time a lot of this type of comparisons, which has shown that some ions are okay, some ions instead need to be reworked, and every single one of these comparisons has led to a new Chianti release. So the collision rates, they're entirely theoretical. There are better rates and worse rates, and then you have to go into at the bottom of the Chianti files, there is the original reference to the calculation, and then you have to go into the original paper and look at the calculation and make up your mind whether this calculation was reliable or needs to be improved. And in Chianti, we worked a lot well, we included all the best in the literature, then the literature wasn't enough, so we started calculating them ourselves, and we strive to do better and better and better, but perfection is not in this world, and so it doesn't belong to Chianti either. And there are some ions which are more reliable than others. So if you have a specific ion in mind, I can give you some guidance, but again, it's all theoretical.
Let me interrupt for a second. I'm gonna open a breakout room because I think Sky would like to ask Barbara Thompson a question separately. And so well, if you want to ask Barbara a question, we'll come to the breakout room that's labeled staff. If you're interested in just listening in on this, just stay here. Okay.
Yeah, thank you, Enrico. The line that I'm looking at is the neon 8 in around 770 and 780 angstrom. So, and when I calculate the intensity also using Chianti and DEM, I took the Feldman abundance file. So that and I verified it with the Skylab observation, which is in Vernes and Reeves paper. So that matches. But when I try to compare it with the more recent observations, like from Sumer, so it kind of varies the intensity, line intensity.
Yes, because that line can be influenced by a lot of different plasmas, because that neonate is a lithium-like ion. It is formed at around the peak, but then it has a high temperature tail, which can also contribute, especially if you're looking at active regions or regions which have an enhanced plasma component at high temperature, then you can have even more neonate. So that line is fairly variable. So I'm not surprised you find variations. In terms of agreement with observations, you can check it whether the ratio of these two lines is equal to 2. And that's the first check of whether anything is wrong, because these two lines are doublet, which is supposed to be density insensitive with a ratio of around 2, give or take. And if it is not, there are some problems in the observations. If they don't agree with other lines, say in a DM or in a synthetic spectrum, then there may be other problems at hand. The lithium-like sequence once had some big problems, in the sense that all the lithium-like ions, oxygen 6, neon 8, magnesium 10, silicon 12, did not agree with the other ions. Now these problems should be solved, but it's quite some time since I last did some check on this. In itself, the collision rate should be relatively accurate, but be also aware that now the intensity of these lines may be a little changed also by ionization recombination processes. The software in chain Chianti has changed, and there are maybe some nuances added by that. I'm not sure whether neonate was one of the ions that was involved in this, but it might also be in the latest version.
Yeah, I use the latest version, and yeah, but the abundance file that is used is that's an old one, like 1992 file.
Yeah, I know that file. Be careful that again, these are representative abundances and not the real abundance of the region that you're looking at. And so different regions will give you big jumps in the intensities of these lines just because their abundance is different.
Okay, thank you.
Hi, Barbara, are you still on?
Yeah, I don't see the room option.
Did I open them? Oh, I gotta open them.
Okay,
There
great.
you go.
Thank you.
Yeah, if you want to talk to Barbara Thompson, why don't you go to room 1?
There once was a star in a galaxy, it was named the sun, and thankfully solar tapestry sends particles high and low. Soon may the solar wind come to bring us plasma and magnetism, filled with hydrogen and helium, and the solar wind will blow.
The solar wind charts a course, pulling lines of magnetic force, flowing outwards from the source, throws particles to and fro.
Soon may the solar wind come to bring us plasma and magnetism, filled with hydrogen and helium, and the solar wind will blow. The earth spun with its iron core, and the solar wind knocks at the door. Magnetosphere screams no more until it must let go.
Once a magnetic line is freed, buckling under the wind stampede, it whips back with tremendous speed, sends particles to the poles.
Soon may the solar wind come to bring us plasma and magnetism, filled with hydrogen and helium, and the solar wind will blow. The particles speed back here and ricochet through the atmosphere, exciting oxygen and nitrogen there, making those particles glow. On and on the cycle spins, sun and earth are celestial kin, dancing to the solar wind, connected by its flow. Soon may the solar wind come to bring us plasma and magnetism, filled with hydrogen and helium, and the solar wind will blow. Soon may the solar wind come to bring us plasma and magnetism, filled with hydrogen and helium, and the solar wind will blow.
Forgotten romantic all my life. 내 주위는 autumn lovely day. 내 눈 속에 비친 aerosol. I'm feeling lonely. 그 말을 끝내고 말해줘요 homie. 다시 crying in my room. 숨기고 싶어. But still I want it more, more, more. I give a second chance to Cupid. 날 믿은 내가 정말 stupid. 보여줄게 숨겨왔던 love isn't real. Cupid is so dumb. 또 꿈길을 걷는 everyday. 눈 뜨면 다시 또 flew away. Waiting around is a waste. 나 솔직히 지금이 편해. 상상만큼 짜릿한 걸까. Now I'm so lonely. 매일 꿈속에서 연습했죠 kiss me. 다시 crying in my room. 포기할까봐. But still I want it more, more, more. I give a second chance to Cupid. 날 믿은 내가 정말 stupid. 보여줄게 숨겨왔던 love isn't real. Cupid is so dumb. I'm so lonely, hold me tightly. 짜릿한 거 원해, really love me truly. 내게 기다림은 없어, I can't wait. 너는 믿지 않아 now, I'm gonna make it mine. Love is a lie, I will show my love is right. It's not a joke, so give it to me right now. No more chance to you. You know, hey, don't worry. 꿈속에 매일 밤 someone who will share this feeling. I'm a fool for love, a fool for love. I gave a second chance to